Good afternoon, everyone. Welcome to this session. Um, on behalf of the Suriname chapter, I'm Elias Acosta, the president of this chapter of the SPWLA. Today we are hosting our first event. We were recently awarded to become a chapter last year in September. And these are our social medias where you can reach to us. This is my team. As I mentioned, Elias Costa, I'm the president. Vice president is Prashant Naigi. He expresses um, um, not being able to be here today. I have Jaswant Uditram, secretary. The treasurer, the money man, will be Vivian Granos. James Deering is our education director, and we have two officers, Daminder Rameser and Farhad Idu, who will be assisting us in different activities. So any chapter has to have a mission, and our mission will be to advance in the science of petrophysics and well log analysis through education, research, and professional development. So we plan to foster collaboration among professionals and in the field, promote best practices, and support the dissemination of knowledge through meetings, publications, and education activities. And that's why we are here today. So having said this, I will introduce our speaker. So Patricia Rodrigues holds a PhD in geophysics from the University Colorado School of Mines. She has a master's and a bachelor from the University Simón Bolívar in Venezuela in chemical engineering. Her experience, she has more than 25 years of experience, and we can break it down into 8 years in PDVSA, Interweb, working in seismic petrophysics and integrating well data through rock physics methodologies. 2 years in Tricon geophysics, where she focused on seismic petrophysics and integrating well data rock physics methodology. 2006, she joined the DRM Energy Corporation and started up the oil and gas company. She worked as a senior petrophysics at I Reservoir, and there she tested and used I mineralysis extensively and provided numerous improvements and suggestions. She completed her PhD while working partially at the Newfield Exploration Company. And between 2014 and 2020, she joined the Whiting Petroleum as a senior petrophysical manager and director of geology and geophysics. And in 2020, she joined the Seispetro as a petrophysical advisor. Her expertise is mineral analysis, and she's instructor of the SPWLA class petrophysical mineral analysis. A course I strongly recommend for any of you if you haven't attended. And now, Patricia, the mic is yours.
Thank you, Elias, for the introduction. And yes, Elias was one of my first students in that class. I don't remember which year, but you were one of the first ones. So hopefully, let me share again. I think we didn't share. Okay. But today I'm not going to talk about multimedia analysis. I'm going to be talking about fracture from logs. And thank you for inviting me, and congratulations on the new chapter. I hope everything goes well. So I know it's a lot of work. I have participated in the Denver chapter, and yeah, you have to do things, but it's really enjoyable and it has a lot of benefits. So, okay, so I'm gonna start now. So this presentation that I'm gonna show you today is a presentation that is part of a class that we teach in it's like a fracture reservoir class. So the people that collaborated in this presentation is Chris Sam, who is a structural geologist from the Bureau of Economic Geology, and Reynaldo Michelena, who works with me, and he's a geophysicist. So the class in general, just to give you a quick background on I would say like the context of where this material you're going to see come from. The class is taught with the purpose of how you build fracture models to do flow simulation. So you have to build a metrics model, you have to build a natural fractures model, you have to incorporate the geomechanical model to get to a flow simulation, to get to a 3D model that can be used for flow simulation. So the talk that I'm going to give today is part of the section about natural fractures model, just the petrophysical part. So what is the petrophysics role in the analysis of fracture reservoirs? And I would say beyond of what is the typical work that you need to do the metrics property characterization. So we're not going to talk about the metrics. You need to do metrics, calculate your metrics properties if you're doing a fracture characterization model. But we're going to talk a little bit here about the kind of things that we do when you're working, when you are characterizing the fractures. So the first part is that you have to do, of course, the characterization. The characterization, for example, can be analyzing the logs to identify the fractures and extract intensity and geometric information. You can also analyze the logs to identify the presence of fractures, and I'll tell you the difference in a second, that can later be used to identify fracture facies or prone to or the facies that are prone to fracturing. So the difference between these two topics, two things here, is that in the first one, you're actually directly identifying the fractures per se. That's kind of, we're going to see that with image logs. In the case of the second point, what we're doing is that we know that they are present, but you cannot count them, you cannot characterize them, you cannot get the azimuth, but you know those the fractures are there, and you can tell which facies are prone to those fractures. Then it comes, that's the characterization per se. Now it comes the part of calibration and integration, which I believe is one of the more important ones when you're doing a model. So we integrate information from logs to define facies prone to fracturing that can be mapped with your modeling techniques, and that can be done with or without seismic. We can integrate log and production data to help in identification of productive fractures. We can, when fracture data is not available, we can help define conceptual models to identify facies prone to fracturing. And finally, of course, we do the calibration of results. So you characterize, help with integration, and then when everything is put together, you go back and calibrate to make sure everything makes sense. So what are the objectives for today? The first one, we're going to discuss how to use log data to identify and characterize natural fractures. We're going to present logs commonly used to help the interpretation of natural fractures. We're going to discuss pitfalls and limitations of different technologies. And we're going to discuss the limitations of estimating fracture porosity from logs. So let's
Sorry,
start.
Patricia, could I very quickly interrupt this very quickly? If we have questions, would you rather we save them till the end?
I think we have enough time. I mean, we can start getting the questions right away. And let me make sure I can see the chat. Maybe we can put them in the chat, if that's okay with everybody. So that way I see the question, like that's how I do it in my class. Just let me put the chat. And yeah, if you have questions, you can put it in the chat, and I will stop when it's a good time to answer your question. So just let me make sure.
Okay, thank you.
I have the chat at hand. Just give me a second. And thank you for the suggestion. I think that's a good way. I'm trying to get the chat in a way that doesn't work. Okay, perfect. Okay, so fracture, so a summary of fracture identification and characterization with logs. Fracture characterization with wireline logs can be quantitative or qualitative, depending on the data available. Image logs are the only truly quantitative measure of fractures. And what I mean by that is that you can actually measure intensity, dip, and strike, while other logs just provide indicators of fractures. Characterization of fractures with non-image logs is typically based on indirect physical effects caused by the presence of fractures. And you're gonna hear the word fractures a lot today. So the robustness of fracture information from logs depends not only on the data available, but also, and more importantly, on the quality of the consistency between the measurements. Okay, so you see, especially when you are not looking at image logs, but when you're looking at other kind of logs, if whatever measurement you have, it has to be consistent. So all the log measurements are really truly indirect measurements of the fractures, but some take a closer look at them more than the others. For example, in one corner here, what I call the direct measurements, we have the sonic or resistivity-based image logs. I call it before like a truly direct measurement, but in reality, we are not doing that, and we're going to explain a little bit more. Then we have the cross-dipole sonic, which is, it can give you information about the fractures, but it's not as direct as the image logs. In the other hand, the most indirect measurements are I would call it like the regular or common conventional logs, like the photoelectric factor, the density, the caliper, the resistivity. And some kind of in the middle, you have mod logs, the sonics, and the temperature data. So that this gives you a spectrum of how reliable the information about fractures is, depending on how close to the fracture or how direct the measurement is in comparison to the rest. So here is a table that I won't read in all detail, but I will walk you through on what is, so in the first column here, we have what kind of log. Here is what we can learn from it. But the third column here is what we're really measuring, okay? And therefore, what are the potential issues? So for example, if you start with the image logs, you have resistivity or sonic logs, image logs. You can measure intensity, dip, strike, relative aperture. But what we're really measuring is that we're measuring the resistivity contrast between the metrics and the fluid or solids that fill the fractures. In the case of the resistivity, in the case of the sonic log, we are measuring the slowness and the amplitude contrast between the metrics and whatever is filling the fracture, the fluid or the solid. So in the first one, if you have like highly productive fractures, when you have the oil production can interfere with the path measurements. In the case of the sonic-based image logs, if you have mineral fill fractures, they're hard to see due to the low contrast between materials. When you're going through, and these are this image log here. So when you're looking at all the other logs here, like the sonic, the PE, the resistivity, and the caliper, what we're really learning is going to be the phases that are prone to fracture. And you can potentially have an indirect measure of intensity. But what you're really measuring is like you're either really measuring the slowness and the amplitude and isotropy in the cross-dipole sonic. In the case of the PE, what we're seeing is that when heavy mud enters the fractures, they will disturb the reading. And it only works when you have birite heavy muds. In the case of the slowness and in the cross-dipole sonic, when you have a formation that have high stress and isotropy, the sonic log will read first the stress and isotropy and then the fracture. So that's kind of a pitfall. And we'll talk a little bit more about some of this in the next sections. So if you go through the table, and I'm not going to read the entire table, and you're going to have that in the recording, you can always check this table to see what you can see with any of the logs. And this is not an exhaustive list of logs where you can see fractures and problems. But like, for example, in the mud log, you can look at loss of circulation. In temperature, you can see lower temperature due to the mud invasion, etc. So the way we're going to go through the presentation is that we're going to talk first a little bit about the image logs. We're going to talk about the cross-dipole sonics. And then we're going to talk about how you integrate these other logs to help you identify these phases prone to fracture. So you're trying to identify where the presence of fractures is and how you integrate that. So let's talk about image logs. So image logs are wireline tools that provide high-resolution electrical or acoustic measurements of the borehole. We have here several different names, and there are many more of this, especially when you get into all base mod, you get like OBMI, etc. It scans the surface of the borehole and provides a picture of the irregularities in the wall. It provides a reliable measure of fracture geometry. It will give you the dip and the azimuth, and it will provide a localized, reliable measure of fracture intensity. And we're going to spend some time talking about why emphasize that it's localized. It may provide information about fracture connectivity. It can tell you if it's open and closed. It will tell you if it's bed bound or it's a through-going kind of faults or mini faults. So there are two, I would call like, there are many types of, I call like image logs, but like let's talk about the big ones, which you would say that the resistivity base or acoustic base. In the case of the resistivity base, these are pads that are touching the formation. So it's important that the borehole is engaged and you have to get a good image. And the image shows the stripes with partial coverage. So depending on the tool that you can have 6 pads, 8 pads. And depending on the borehole size, the distance between the stripes is going to be greater or smaller. Sometimes you find the more adequate number of pads depending on the caliber of your borehole. In the case of the acoustic image, it gives you it's a rotating tool with a centralizer, so it will give you a continuous 360 degrees images. I really like the acoustic base tools because they are kind of easier to understand, easier to see. It doesn't show certain features, like if you have resistive, like fractures that are filled with material, sometimes it won't see it because it has the same property than the metrics and that kind of thing. But when you're trying to map the open fractures, it's usually a pretty good tool. So the way to interpret the images, you have the borehole. So the image basically starts in one point and finishes in the same point. It's kind of like you are unwrapping the circles. You start, here you can see you go north, east, south, west, and north. And if you have a vertical well, the fractures look like a sinusoid. But if you have a horizontal well, near vertical fractures will look like a sinusoid in a vertical well, and they will look like straight lines in a horizontal well. Other features that you can get from image logs, if you have, and this is in the case of the vertical well, as I said, the natural fractures will look like sinusoids, especially if they are near to vertical. If they are, a little bit more deep in, the sinusoid doesn't have that much amplitude. The stratification will look horizontal. You can see the layers here. If you have drilling-induced fracture or tensile fractures, they are going to be parallel to SHmax, and they look like straight lines, kind of. No, they're not straight, definitely, but. And if you have breakouts, it will help you also to learn about the direction of SHmax. Sometimes you have both breakouts and tensile fractures, or you have one or the other. In the case of fractures from horizontal wells, so the natural fractures appears as a high dip, straight lines, and they are oriented perpendicular. If the well is oriented to the perpendicular to the fractures, and the stratification will look sinusoidal. So in this case here, we can see like this fracture, this is actually a fault, and the stratification will look like a very high amplitude sinusoid here. The drilling-induced fractures can be vertical, also parallel to SHmax or parallel to the well bore. They're kind of harder to identify here. And when you see bed displacement, you can see that it falls. So you can see here how the bed, this is stratification, you have displacement, so you can interpret this as a fault. The beds also help you see like these bed-bound fractures as well. You can also differentiate if they are open or partially open fractures. You here see open fractures. You can see the dark color, in this case, the low amplitude. This is a sonic image log, an acoustic image log. So you can see the low amplitude due to the fracture. But when you have a partially open fracture, you can see that, it's open in certain sections and then it's closed and it's partially open over here too. So how is the image logs, how they are represented? Is that just a typical one? It will give you, in this case, they added also the lithology. You have usually an image of a picture of the image log, which typically doesn't help much at this scale. So you have to find the right one. And it will give you the tadpoles, which represents, in this case, the location of the I would call like the circle here, represents the deep of the, like the angle with the vertical. So if it's 0, it's a vertical fracture. If it's 90, it's a horizontal fracture. So how far from the vertical is how much deep how much the fracture is deep in. And the direction of the tail will tell you the azimuth. So typically you see the fractures here, and you see the well, depending on what it is. This seems to be the fractures that are 90 degrees. Sorry, in this case, the 90 degrees is I had it backwards. Sorry, the 0 here, it depends on how the angle is defined. So sorry, 0 here is the stratification, 90 is close to vertical fractures. So you can see the vertical fractures here in blue. And in the next strand, you see the fracture intensity. It's kind of like a fracture density number. So they count the number of fractures in a certain window, like per foot, or in this case, it's per meter. You have Rose diagrams that represent the azimuth and the strike of the, or the strike of the fracture. So you have this representation as well. Okay, so a quick question, and I will ask you to answer in the chat. Since we're not too many, we can do that. So when, before we talk about other details about image logs, we have a case in which we took 95 cores in a reservoir in an area, and 95 out of 100, so like 95% of the cores don't contain a fracture. So these are vertical wells, they did not contain a fracture. And we had 100 image logs, and of course this was put in percent. I know that exactly was not the case. And 88 of the image logs did not contain a fracture. Would you call this a fracture reservoir? When 88% of your wellbore images doesn't have a fracture and 95% of the cores did not have a fracture? Just if you can answer in the chat, yes or no, to see how much we're doing. One no. Anybody there, or you're trying to find the chat? Please, let's see. And you can answer only yes or no. It could be yes. I knew James. I know. I know how you're thinking. Okay, yes. Another yes. A lot of people are saying yes. Okay. I think James put everybody to think about that. Okay. The answer is it could be, like James said. What happened, of course, in the case of this data, came from a reservoir that looks like this. This is the outcrop of the reservoir, which was actually extremely fractured. It's just that all your wells are vertical, so you have a bias in the sampling. Okay, so this is extremely, as I say, extremely fractured with average spacing between 10 to 15 feet. But it's just that when the wells are vertical, you have a hard time sampling the vertical fractures. So let's talk about limitations and pitfalls of image logs. One of them is sampling bias. So you will undersample fractures that are parallel to the wellbore. So in vertical wells, you will underrepresent the near vertical fractures, so you have a deep bias. But when you are in horizontal wells, you will overrepresent the vertical fractures, and you will have a deep and an azimuth bias, because it depends on the borehole and the orientation of the borehole in the case of the horizontal. Some areas are better sampled than others because it depends on well coverage and distribution. And just a fraction of the reservoir, really, of the fracture network is being sampled, which is just the volume of investigation. The other, excuse me, the other limitation we have is the aperture overestimation. Is affected when you try to measure aperture, and we'll talk about that. The aperture is affected by the borehole condition and does not represent the average aperture of the fracture. And you have, of course, interpretation pitfalls. It's a subjective bias. Basically, we have different people, so you have inconsistency of image log interpretations between wells. You have misclassification of fractures if they're open or closed, if they're bound or through going. And you have fractures versus bedding if they are difficult to separate when they are subparallel, when you have like near horizontal fractures and you have a stratification, for example. So let's talk about the sampling bias and something that is called the Terzaghi correction factor. So this is an example here. If you have, this is the same formation with the same number of fractures, and you have a well that goes through the bed, it will see only one fracture in the vertical section. But when you go through the horizontal, it will see 10 fractures that are intersected. But the actual fracture intensity in both beds is exactly the same. So there is a correction called the Terzaghi correction that will correct it will give you the real number of fractures as an angle of the fractures to the borehole. So you have this is the borehole in the case of a vertical, and you have a fracture that has certain dip, and you calculate the angle between the normal to the fracture, the normal line to the fracture, and the borehole. Okay, this is how the angle is defined. Could have been defined differently, but this is how it is. And so the real number of fractures will be whatever you measure multiply by a factor called WT, and that WT is equal to 1 over the cosine of that angle. Okay? So how that looks is here we have several curves just as an example. So this is going to be the correction factor, the WT, depending on the fracture dip. So basically what is the inclination of this angle here. And the wellbore inclination, we put the example of if it's a vertical one, which is the dark blue here. If it's a horizontal one, which is the intermediate blue here, and the light blue will be a 45 degrees inclination borehole. So the way to read this is that if you are in a horizontal well, any fracture that that is horizontal, basically, that the dip is 0, so that's parallel to the bedding, you have the greatest correction because it's parallel to your wellbore. So basically, you have your fracture and the wellbore at the same inclination, and you have 0 correction. It's multiplied by 1, so it's a 0 correction when you have a vertical fracture. And the contrary is, of course, with the vertical wells. So for vertical fractures in vertical wells, you have the highest correction, and it goes to 0 correction if you have horizontal fractures. In the case of the 45 degree, then it's something intermediate. So the fractures that have the greatest correction will be the ones that have also 45 degrees. So they are parallel to the borehole. Okay, Terzaghi is assuming that the fractures are regularly spaced, although the wellbore structure.
Sorry, all through.
Through. Sorry, all through the wellbore
my
structure.
bad.
No, it's okay. This correction is applied, through the borehole. So you will have like an intensity. Imagine. Let's go quickly here. So you have this fracture intensity here. So you take that fracture intensity and you multiply by the fracture, by the factor. And of course, you may have by a varying inclination for the fracture. So the way to apply it, I know it depends. And I know Chris Sam is an expert doing this. So if you need more information, I can ask him. But you basically correct the intensity log in your borehole. Because the borehole will change inclination sometimes. So if it's just that the example that I put here, kind of how the equation behaves, but the equation can be applied to every cell, for example, in your borehole to correct for that. And this is something that you apply to your, imagine that you have an intensity, the fracture intensity here. So the correction here is going to be different than here because it has 45 degrees here, and it has a different correction than if it's here. So here the correction will be like this really large one because you have almost vertical fractures in a vertical well, and here you have kind of close to vertical fractures in a horizontal. So the correction will be almost zero here. I don't know if that answers your question. Hopefully it does. So, and here I have an example actually. With the fracture frequency per 10 foot. And this is a measured depth. This is in a vertical well where we have large correction. So you have the depth here in red. So this is your intensity log. And after you apply the correction, you get the blue bars. And this is the same correction applied for the horizontal well when we got a small correction. So you have the uncorrected is the red, and the blue is the corrected one for the same, not the same, but these are both vertical fractures, I believe. Yeah. So it's a combination of, it has a lot of math because you have to have the orientation of the borehole, you have to have the orientation of the fractures and the intensity, and then you can apply the correction. Okay, so let's talk about aperture. Well, sorry, let's see, I see James. The question about James is the theory was validated. Yeah, there is a reference about that, Meller, and I could probably find you the paper. I know this is something that when we build fracture models, we need to take into account. Basically, when you're doing fracture geologic models, there is a lot of uncertainty in any places. So one thing that we definitely need to know, that we know is this. And what happened is that, imagine that you have, as I said, the example about the fracture reservoir, and you're trying to map fracture intensity using vertical wells when the fractures are vertical. So you know they are wrong. So this is one way to account for that. Now, the details on how much is the correction, like this number here, like this correction cap is applied, and you could actually change it, but you use it to improve the model. But I don't know the details about the paper, so, but if you are interested, let me know and I'll find it for you. Okay, aperture from image logs. It's usually not appropriate when you're trying to do fracture porosity calculations. It tends to overestimate the aperture of the fractures because it is affected by roughness and washouts near the well, near the wellbore region. So it has like image artifacts. So basically what is happening here is that what we're seeing is just when the fracture crosses the borehole. So near the borehole, since you have the fracture, it tends to usually kind of be more open than it is in the average, or is expected to be more open than along the fracture. So I will tell you how we usually, I would call like how we calibrate the aperture. This aperture could potentially be like a good aperture index. So if you want to see which ones are more open than others, it can tell you that information, but not necessarily be used for that. Because as I said, the roughness and washouts usually occur in that intersection of the fracture with the borehole. Regarding interpretation pitfalls, and this is an example of a project that I work with. I had several wells, with log image interpretations, and in this case were different interpreters for each well. And I think like some of them have one interpreter, some others have a different one. But also I noticed that when you have a highly fractured well, depending on where the interpreter started, if it started, at the top or at the bottom, you will see more fractures interpreted, they just get tired of interpreting fractures along, after a couple of hours picking fractures. So and this is an example, we have these red lines here that were interpreted by the service company, but you can definitely tell that there were more fractures that were not interpreted in the image. So sometimes you are doing a calibration, but you have to do a quick, even if you are not the one doing the image interpretation, you should do a quick QC of the fracture interpretation. Okay, so let's talk about sonic waves response to fractures. Sonic tools measure the speed of propagation of the wave through the formation. So unlike nuclear tools like the gamma ray neutron and density that measures, I call like atomic particles, sonic waves are sensitive to the microstructure or texture of the formation. The microstructure of the rock has effect both in velocity and amplitude. So what I mean by that is that in the case of the cross-dipole sonic, you have your borehole here, and you have your dipole, so you have fast and you have the shear wave that is you have in two directions. So you have one that is gonna orient what we call like the slow velocity and one to the fast velocity. It goes in two directions. So what is happening is that your sonic tool is gonna try, if it goes, this is the shear wave. So the shear wave, the polarization of the particles goes in this direction. So for this, of course, vertical well, okay? So you're going this direction or in this direction. So you send it in two directions. So it cannot go, like if you have a regular sonic tool, like the P-wave sonic tool, the polarization goes, like in the vertical direction, okay? And we're gonna talk a little bit about that when we talk about porosity, sonic porosity index. So what happens here is that when you have the slow shear, it has to go, the particle moves across the fractures. So if the fractures are filled with liquid, so they're open fractures, it's going to be a slow movement. But if it's parallel to the fractures, it's just seeing solid rock. It doesn't see any presence of fracture, and that's the fast shear. So it measures velocity and amplitude between the two of them, the fast and the slow. And there are also more advanced, more recent tools that include what we call dispersion analysis, which can help identify the cause of the anisotropy. If there is a difference of speed, a slowness between the two directions, you need to further analyze further analysis needed to determine if the anisotropy is due to fractures or stress. And why do I say that? Because I explained this in the case of fractures. So if you know you have fractures and you don't have too much anisotropy, stress anisotropy, you can tell that that difference between the fast and the slow is due to the presence of fracture. And of course, the anisotropy is what is the measure of the difference between the two. Basically, like you have a different velocity in one direction than the other. What happens when you have a stress, and I'm going to leave that to the pitfalls, but sorry, no, let's finish this up here. So when you have a lot of stress, what it means, and I'm going to do another little picture here, is that you have, and I'm going to put it like this, you have a lot of, you have SH max, and you have, let's put it here, thinner SH mean. When you have a big stress anisotropy in between these two, what happens is that your pores also align with the stress and your grains. Everything deforms in a way that even if you don't have fractures, you're going to see a difference in shear velocity between the two directions. If the difference between these two is large enough, even if you have some fractures, what you're really measuring is the difference between stress. Also, what I mentioned here in the second bullet point, as I said, there are some more recent tools that measure dispersion analysis. And dispersion analysis is basically looking at the change in velocities and amplitudes with frequency of the tool. And that's a much more advanced tool. I have seen some results only once in one well. And based on that dispersion analysis, they could tell you if the anisotropy that you are seeing is due to stress or due to fractures. This is just an example of a cross-dipole tool. So it will give you the slowness, the dt of the slow shear, or so the shear slow or shear fast. So you can plot them in the same scale, and if you color between them, you could see that where do you have more stress anisotropy. This is just the full waveforms here, and this is the calculation of anisotropy. You see more anisotropy at the top. And again, this could be caused by fractures if you're sure it's not caused by a stress anisotropy. Okay, so the limitations, as I said, as I already emphasized here, is that you need additional data to explain the cause of anisotropy, if it's stress or fractures. It can provide orientation, because when you calculate, and I forgot the name that you use for that, but you can calculate the direction of the highest anisotropy, and it will give you the strike. It won't tell you that true deep, it won't tell you the deep. It will tell you the intensity indirectly, because the degree of anisotropy could be a measure of intensity. But it assumes a single family of vertical fractures. So if you depart from this assumption, it may yield to erroneous results. Like, for example, orthogonal system of fractures that can be highly permeable might be missed with the cross-dipole sonic. And basically what that means, if we go back to this picture here, is that imagine that you have fractures in this direction and any other direction. So for the two shear waves, if they go in one direction or the other, they're going to see the same velocity, but you are in a really highly fractured area. Okay. Okay, so let's move now to other wireline logs. As I said, we're going to talk about three different groups here. We're talking about the image logs, we talk about the sonic or the cross-dipole sonic, and we're talking now about other wireline logs. How can you be used to identify fractures? It's the most indirect measurement of fractures. Identifying the fractures is based on what I call disturbances of the signal, and which means that understanding the typical response or character of the logs is required to identify those disturbances. It is sufficient for fracture identification when these disturbances are found in several logs. Typical logs that are used are, you can have resistivity, density, caliper, mod log, PE, temperature, etc. For example, is that you can find washouts in tight intervals in a carbonate, for example, that have severe mod losses, and you can probably you can classify that as a good indicator of fractures, because it's tight, so you know the losses are not due to porosity, so they must be done due because of fractures. The fractures are seen primarily on tight intervals. I'm going to show you an example. But when porosity develops, we don't see the fractures. Even though maybe they are still in a shear zone, you don't see the fractures because the deformation can be accommodated by the grains and the pores. And sometimes they're there and you just don't see it in the measurements. It will, looking at other wireline logs, it will allow you to identify fascias that are prone to fracturing. And it can be, again, an indirect assessment of fracture intensity. That's more like a stretch. It would be only in few occasions we can see that. And then the fascias prone to fracture can be mapped when multiple wells are present. So there is no, in the case of looking at fractures with other wireline logs, there is not an exact recipe. I'm going to show you an example of that so you can see how they look. But it will, as I said, you have to basically do two things. One, say, well, how a rock looks when there is no fractures, and what it means when it has fractures. This is one well here where we did the formation. So we had, I just realized that. Yeah, this is a track where we have gamma ray, we have density, porosity in the second track. We have fascias from neutron density cross plots in the third track, and we have the resistivity logs in the fourth track. So we see one interval here that has washouts or what we call like a roughness in the caliper. I mean, this tends to be a good caliper. It's not like an impressive problem with the caliper, but we see that we have density log issues. This is the porosity from the density log, and the other one here is one that we model to eliminate the washouts. And we see here that for the resistivity, we see like what we call a flat resistivity with a large invasion profile, kind of like a short circuit. And I'm going to show you how we saw it in several wells. We also see in the same interval that we have loss of circulation reported in mod logs. So we could then now call, and this gray area here is the area that we consider that we know the fractures are present, but we didn't have image logs to see them. So what we did is that in a fracture area, we use facies flag. I mean, the interval of interest was this one here, so we just flag in which wells we saw that kind of behavior. And of course, I show here the example where we saw the fractures. Not in every area we see the fractures. Limitations, of course, of using other wireline logs is that we need to understand the reasons for the perturbation. That is not, like other kind of, like a lithology change, a porosity change, or just, errors in the tools. That if you find a disturbance or a change in a single log, it's not a reliable way to identify the fractures. You require information from different type of logs to make sure that that's actually due to fractures. It doesn't provide any information about fracture geometry, dips, or azimuths. If disturbances are found in different logs, we can conclude that the fractures are present, but the contrary cannot be affirmed. So basically, if you find these, signature changes in all the logs, yes, there are fractures, but if you don't see it, you don't necessarily know that there are fractures. Like in the example before, there are other sections like this that you are not 100% sure that they are not fractured. It's just that, maybe the mud system was better and you have a better engaged borehole, so all your logs behave well, even if there are fractures present. So again, it can help with the calibration, but it's just an additional tool. This is also an example. One thing that we recommend always is to use this kind of montage. I know that we petrophysicists do it a lot in many cases, but this is not only logs, it's other information, like you have your typical logs here, you have the fluid loss from the mud logs, you have the information from the image logs. And in this case, what we did was not only to identify where fractures were. In this case, we were looking for open fractures, or it was not really open fractures. We were looking actually for fractures that were contributing to flow significantly. So not only the image log will tell you they're open, but also which ones are really conducting a lot of fluid. So having the mud losses here was really important for the interpretation. And sometimes we also include, as I said, the PE is always a good tool as well to see that, because sometimes the mud goes into the fractures when you have losses, and will show you a peak like this. Okay, so the last topic that I want to talk about here is fracture porosity from logs. In most reservoirs, fracture porosity is very small. It's usually overwhelmed by the matrix porosity. Exceptions are when you have in igneous or metamorphic rocks where there is no matrix porosity. Fracture porosity is estimated usually by reservoir modeling. At least in our experience, that's the more reliable way to do it. And it is related, and that's why it's so important to calibrate the intensity. Some techniques claim, use that they can measure porosity from wireline logs, and what I mean porosity, I mean fracture porosity from wireline logs, but they are more like fracture indicators. And one of them is the sonic versus neutron density porosity to estimate secondary porosity. And I'll explain a little bit more why it's not necessarily a reliable way to do that. So, as I said, in many instances, especially when you have a lot of matrix porosity, the fracture porosity really becomes some kind of noise. Like we We have, when you are measuring the porosity from your neutron density logs, you're measuring both the matrix and the fracture porosity together. But the fracture porosity is so small that it's really hard to differentiate between them. When, as I said, when you're in systems where there is no matrix porosity at all, then whatever porosity you are measuring with your neutron density is actually your fracture porosity, and you have it. That's kind of straightforward. So why my issue, I would say, between using the sonic secondary porosity index as a measure of porosity? As I said, it can be an indicator, but not necessarily I would call like an absolute number. So the theory is that, which is a very strong theory, that as I mentioned before, the sonic travels through the solid rock. The sonic, like the P wave, not the shear, the P wave. It will go through the fast path, avoiding the fractures. So the rock is going to look harder than what it is. Theoretically, the sonic porosity will be then lower than the neutron density porosity in the presence of fractures. It will also be valid if you have like buccal porosity as well. So anything that is isolated, the sonic log will go through the hard part and will avoid that. The important assumption that we have here is that the matrix porosity that you can calculate with the neutron density logs will be exactly the same than the sonic log, which will be only valid for wily rock types. And what I mean by that is that in the presence of, I mean, like I would say, like, this is valid, and I have seen it working only when you have like a pure limestone. So you have a single, you just have only one mineral. So when you calculate a neutron density porosity, you're in limestone matrix, you have a really good porosity. And also when you're going to calculate the porosity from sonic, you know exactly the delta T, or the slowness of your matrix. So in areas where there is no fractures, you're going to see an overlap. This here porosity index is the difference between the matrix porosity from density, is the difference between the neutron density porosity and the sonic porosity. And this, I would go like this here is the secondary porosity index, can be showing you the probability of fractures if you know there is no buccal porosity of anything. The thing is that the assumption here is, I would call it like too strong. It's like there are only few cases when you're going to be working in fracture reservoirs where this assumption is really valid. So even though you can use the secondary porosity index as an indication, but not necessarily as a quantitative way of measuring how much porosity from fractures you have. The way to do that, and I'm not going to go in detail about this plot here, is how I would say like our reservoir engineer explains how you get really porosity from fracture. And the way to do that is that the porosity from fracture is going to be your aperture, and imagine that this is a block in your simulation model or in your geologic model. So you have the length of the block, the height, divided by the total volume. So you can calculate, imagine you have this volume here, and you calculate, basically you're measuring the open space in a fracture reservoir. It is calibrated with production test and simulation. And actually, I want to go through here. This is how much fracture porosity, depending on the aperture, you calculate in one of the models that we have done. So the porosity is between 0.07 and 0.33% porosity. So these are porosity units. So, and as I said, if you are in a carbonate reservoir that have 10, 12, 15% porosity, this becomes the noise in the porosity estimation. And that's what's so important, to calculate fracture porosity in a different way. So I'm almost done here. I have 4 more sites. This is what we talk about the petrophysics role, and I'm going to go just this petrophysics role in analysis of fracture reservoirs. As I said, we work in the characterization, as I said, like how we measure it, how we know the phases, and that's what we have discussed in the previous slides. In the calibration integration, it varies significantly depending on the project. I'm going to show you like 3 slides that are kind of part of the analysis on how we work with the calibrating results or estimating phases. And so the first one here is it's a plot that actually Chris Sam, the structural geology, uses significantly. And we did this project maybe 10 or 15 years ago. And what it's been amazing for him is that this assumption that I'm going to tell you about in a minute, he has seen it in many other areas as well. So what we did here was a neutron. This is the neutron density cross plot. We have your sandstone, limestone, and dolomite lines. And the points that are shown here is only the conductive or partially conductive fractures that we saw in the FMI. So based on this, we selected 8% as a cutoff because the 8% had here the 94% of the fractures. So 94% of the fractures that we saw in the FMI were found when the rock was tight, but the tight here was defined at less than 8% porosity. We also defined another two phases in the project, the limestone and the dolomite. So what I was mentioning is that 8% seemed to be a cutoff that he found out that after many years working with other projects was very consistent. I know there are other areas in which the 8% doesn't stand, but it's really good to look at data this way so you can put the select your cutoff. Another way to see this is the fracture density, how much fractures per foot versus the matrix porosity. Okay? So, and this is another, this is an area, actual result from a reservoir onshore that I did in a project. So you can see how the fracture density decreases with porosity. And again, this is a different project, and you see at 8% more or less, the fracture density decreases significantly. What is interesting too is that for the most unconventionals in the US, you are really in these low porosity zones. And you can actually always assume that they have some kind of fracturing. I know we have, some of them you have a lot of clay or a lot of kerogen that will reduce the amount of fractures. But if whenever they don't have too much of those more ductile materials, you can assume that you have significant natural fracturing. And this last example here, I'm going to go first explain the tracks here. So the tracks is that we have, in the first track here, we have the open fractures in blue. We have closed fractures in orange. And we have two different measurements from seismic. Okay? So the red is the seismic curvature, and the black is the seismic strain. They're both measure basically how much the formation was deformed. So here in the right, what we see is the lithology. So that's the other piece that we need to integrate. Because we can see that there is a good correlation if you look only at the first part of the reservoir here, that when you had more strain and more curvature, you have more open fractures, which is the blue here. You have less, you have only closed fractures. But of course, after this section here, there is no correlation. You actually have here more deformation and there are no fractures. But that's actually due to the increase on clay content, which is the yellow. As I say, if you have ductile material, you won't have, the fractures won't develop, even if you have the deformation. So whenever you are using, the way we integrate when we're looking at the models is that we use seismic information to help map the intensity, but it has to be a combination with your lithology and with your facies that are prone to fracturing. So in the model, we classify this as a ductile facies that doesn't fracture when we are distributing the fracture intensity using seismic. And with this, I'll finish my presentation. I don't know if you have any questions.
Yes. Thank you very much, Patricia. So we open for question.
I see somebody typing. And if you want to use the mic, Francisco, that's fine too. the chat was while I'm presenting, but whatever is easier.
No, I don't have any questions. Just I would like to thanks for your time. It was very interesting.
Okay. Yeah, and if in the future you have any questions, you can also email me. That will be good as well. And I understand.
Patricia, while people maybe put your question in the chat, I have some. I don't know if it's a question, but maybe something we can partially discuss here.
Mm-hmm.
So I also have been working something similar, not so detailed, but and one of the things I think you mentioned about the interpretation, classification of fractures using image logs. I saw you in your presentation, open, close, then conductive, not conductive, partially.
Mm-hmm.
Um, is this something that has been already standardized in the industry, or still depends on who does the interpretation and the service company?
Well, I don't know if I don't think service companies are the same. I mean, I keep finding it's just that since I work as a consultant, when I get image logs, there are different vintages. So there are interpretations that came from 5 years ago or 10 years, and then one that was, like 1 year ago. So they still, they are usually, I call like internally consistent. So if you're working with image logs from Schlumberger, they're probably how they call the fracture, they are the same. And what you have to do is to try to find equivalence in whatever other service company. And for example, in our case, when we're doing fracture models, we are worried only in distributing what we call open or partially open fractures. And that means that they are, that's not true anymore. And anymore, no, it means that if you have hydraulic fracturing, they can actually, the ones that were closed were actually open. So depending on the project, we also distribute, we'll just distribute every fracture, and then we see which of them are active depending on the geomechanics regime they are, and we calibrate with the image logs. But I would say, to answer, quick answer, I don't think they are consistent. When they call it through going, they also call them sometimes faults, even though they are not large faults. They are just called faults because they cross the entire, they cross the stratification. Sometimes they call bed bound. They have another name for that, and which I forgot right now. So basically, answer no. You have to find how they're called between the different companies. Okay, so a question here. Based on my experience, what are the best seismic attributes that correlate with the presence of natural fractures in the reservoir? The one that we like the most is actually the strain. A lot of people use curvature, and sometimes we do as well. But the strain is the curvature is the second derivative. I mean, if you have a plane, you calculate the first derivative, that's the strain. The second derivative is the curvature. So we tend to like more the strain. We have seen better correlation with, because we calculate, and there are two things that we calibrate. And both of those attributes are, for us, the best ones. I would say that we tend to use sometimes more the strain. But in certain instances, depending on how much folding the formation has, the curvature can be a better indicator. So I would say that test both of them. We usually do not use like velocity anisotropy, as I said, in seismic. It has the same issue that we have in the cross-dipole sonic, that if you have too much stress, it can be an indicator actually of stress. So you need to be very careful with that. Okay. Well, it looks like there are no more questions.
Yeah, there are people typing. So I have another comment question. I don't know how to classify it, but have you used like full wave sonic using the chevron shape to maybe indicate that you have something there, like might be a fracture?
You mean like the other measures of the sonic, or I would say the answer is no. I usually get the sonic already processed from the service companies. So if they did the analysis, I will take a look at that because I don't usually go and process the full wave sonic for that. I have seen examples of using the Stoneleigh wave as an indicator of fractures. And I remember working with a service company once that they were doing this, I call like different analysis of the Stoneleigh wave to indicate fractures. And it was more like a 50-50 match. So I wasn't very happy with that. Definitely, it's always good. I mean, if there are new techniques, they're definitely worth trying them because the sonic may be a good indicator of fracture. So, okay. So, question: is there requirement to have density difference suitable fracture for suitable fracture identification? The answer is no. I mean, as I said, what is important is that you see differences in more than one type of log. The example that I show, we had again there was a problem with the borehole due to the presence of fracture that translated into a problem with the density. But I have seen, for example, that you have a good density and you have a good neutron and you had a good PE, but then the PE have really large spikes because the mud had barite, and you can see how the mud will invade in the fractures, and those was the indication of fractures. But you could also see like a little spike in the caliper. I mean, you have to go understand what the change is, and sometimes it has a density change, sometimes it doesn't. So.
But thank you, Patricia. But I could see on one of your slides that the tighter the zone, the more, should I say, easy the identification took place, or?
Yeah, and that's just that the tighter the rock, and that was for this, I think it was that example. No, let me see, what's the next one? Well, I forgot which one was. But what I mean by that is that if you go through this plot, and as I said, we have seen this behavior in many reservoirs.
Yes, so indeed. This slide, I mean.
Yeah, the tighter the rock, it's more prone to fracturing. It's just like like rock mechanics type of theory. So when you and maybe I misunderstood your question. So what we're really looking here is that if it has like high density because it's tight, then it is more prone to fractures. Like in this example here too. There is a larger chance. I mean, if you have low porosity rock, there is a higher chance that you have fractures. It's just that but that's not the entire picture because you need to know if you have clay as well. You can have low porosity, but you have a lot of clay, then your rock is ductile and then it doesn't fracture. So there is no as I said, there is not a set recipe. You have to integrate all the information to come up with a good interpretation from logs.
So I have another question. Might be the last one if no one else has one. You mentioned about the fracture porosity, no? And I saw very, very low values. But I know that these very low values in terms of permeability might give you much more permeability than from the matrix. Is there a model to estimate this permeability? Because if I introduce those small values to the equation that we normally use based on Timur, it will not be significant in terms of permeability.
I would say that I don't have an answer for that question exactly. I know that, I mean, like from logs, I never try to estimate a permeability from the fractures. Like I may know that the fascias that have fractures will have more permeability. But when we do models, when we do the modeling, we have a dual porosity model. So you get, you try still to establish the permeability from your matrix because we need that when you're doing a simulation model. But then the fracture permeability is really depends on the aperture of the fracture, and that's a tuning number. I mean, that's tuned with, you need like a production test or actually production data. And what we typically do is that we have you have your geomodel, you distribute the fractures, you calibrate the fracture intensity and the dip and the azimuth based on the log information, and if you have microseismic, with seismic as well. So when you have all your fractures, first you use your mechanics to know which ones are open or closed depending on your stress. And then the aperture will give you how much permeability they have. And that's when, and that's calibrated with simulation. So if you want to do something in the logs, I think it would be more like an index. If you have more fracture intensities and they are open, you will have more permeability in those intervals, but you cannot necessarily, well, I mean, maybe you can, but I don't know how significant would be for the analysis. It's just more like telling somebody that the rock is more permeable than the other. But okay. Well, thank you all for coming to talk. I see Fabian. I don't know how you pronounce your name. I pronounce it in Spanish.
Fabian.
Fabian, okay.
No, I would like to thank you. That's was busy typing.
Okay. Thanks so much.
All right, Patricia, I think there's no more questions. And yeah, on behalf of our chapter, we would like to thank you for your talk today and willingness to be our first guest. And we appreciate your time here with us.
No, thanks to you again. Congratulations for the new chapter and good luck in the future.
Yeah, thank you.
Thank you. Bye-bye.
Bye.
Thank you, Patricia.
Thank you, James.
Thank you.